from the definition of characteristic function, we know that it has some relation with the distribution function of a random variable. That means, given a random variable and given a distribution function, we can find a characteristic function. Now, I have already mentioned that the main question is it possible that to say that characteristic function really characterizes a distribution or rather a distribution function. So, that means we know that when there is a distribution function, we can always find the characteristic function. But what about the other way around? That means, if I give you a characteristic function or if I give you a function which satisfies the properties of a characteristic function, and hence let us say that this is a characteristic function, can we find a distribution corresponding to this characteristic function? That means, can we find a distribution function for which this would be the characteristic function? If it is possible to find such function, the natural question will come that whether we can uniquely identify that distribution function. One can go one step further to ask, given a characteristic function, is it possible to derive the distribution function? So, we will be discussing all these things today in this class. So, characteristic functions 3. We have already discussed some properties, definitions and couple of theorems, interesting notions about characteristic functions. First, let us consider one small example. Suppose x j is a random variable that follows binomial 1 with parameters 1 and p, and j equals to 1 to n, and all these x 1, x 2, x n, they are all IID random variables. Then it can be easily shown that the characteristic function corresponding to this random variable x j, which is phi x j t, equals to q plus p into e to the power I t. Let us define a random variable x, which is nothing but sum of all these x j's, that is x 1 plus x 2 plus x n. And we have already seen applications of this kind of sum of random variables in statistics. Then the characteristic function, so the question is it possible to calculate the characteristic function of the sum of random variables from the characteristic functions of individual random variables? Since they are independent and fortunately in this case they are identically distributed, so characteristic function of x can be written as phi x t, which is expectation of e to the power I t x, which is nothing but expectation of e to the power I t. If we replace x by summation x j, then we can write this as product of e to the power t x j, and since they are independent, that means x 1, x 2, x n are independent. So, e to the power I t x 1, e to the power I t x 2 and so on, they are also independent. So, this product comes outside the expectation. So, it becomes product over j equals to 1 to n expectation of e to the power I t x j, which is nothing but product over j equals to 1 to n phi x j t. And if you just replace this phi x j t, which is q plus p into e to the power I t, then this becomes q plus p e to the power I t whole to the power n. Actually, this we can say that just by convolution theorem we can get. And if we look at this characteristic function q plus p into I t to the power n, we know that this is the characteristic function of a binomial random variable with parameters n and p. But the question is, from this observation, can we immediately say that x follows binomial n p? So, this is the basic question that we are trying to address in this talk. This actually triggers a general question that does there always exist a distribution function corresponding to a characteristic function? That means, given a characteristic function, can I find a distribution function for which this would be the characteristic function? Second question, if this exists, is it unique? That means, if the distribution function really exists corresponding to a characteristic function, is it really uniquely defined? So, we are trying to address the question, these two questions in this discussion. To to elucidate this thing, we will use one important theorem which is known as inversion theorem. Let us see what this inversion theorem states. Let phi and capital F be respectively the characteristic function and distribution function of a random variable x. Let A and B be 2 points of continuity of f. So, note that we are considering two points alpha and beta, and both should be the continuity point of f. Then we can write capital F of beta minus capital F of alpha equals to limit sigma goes to 0 1 by 2 pi integration minus infinity to infinity phi t e to the power minus sigma square t square by 2 into e to the power minus I t beta minus e to the power minus I t alpha divided by minus I t dt. So, this actually states that there is a way through which we can get a distribution function, that means we can get the expression of capital F from the characteristic function phi t. So, let us discuss the proof of this theorem, at least the outline of the proof. But remember, this expression involves two things, one is the integration, another is one limit. So, after integrating we will get something which, and when you take the limit of that expression as sigma tends to 0, what we get is the distribution function, or rather capital F beta minus capital F alpha, this probability. That means, this gives you the probability that x lies between alpha and beta. So, for the proof, just recall what we have learned in convolution theory. So, let us consider the convolution of two distribution functions. One is the f, that is the given distribution function of a random variable x, and capital phi of sigma, which is nothing but the distribution function of a standard of a normal random variable with mean 0 and variance sigma square. So, capital phi sigma is a distribution function of normal 0 sigma square variable, and let us call this convolution, let us denote this convolution by capital F of sigma. And also consider two random variables, one is two random variables x and y sigma, and define z equals to x plus y sigma. X is our original random variable, and this y sigma, we take this y sigma to follow normal 0 sigma square. And also we assume that x and y sigma are independently distributed. Naturally, since y sigma follows normal 0 sigma square, the characteristic function of y sigma is e to the power minus t square sigma square by 2. Let us define one function which is phi of sigma t, phi sigma t equals to e to the power minus t square by 2 sigma square into phi t. This thing, it is easily seen that this is integrable, because mod of phi t is always less than equals to 1, we have seen in the last few classes. So, small phi sigma t we define as e to the power minus t square by 2 sigma square into phi t. So, these are basically we are assuming some of the things here to prove this inversion theorem. Then consider this integral 1 by 2 pi integration minus infinity to infinity e to the power minus I t x phi sigma t dt. Now, what is phi sigma t dt? We have already seen that this is e to the power minus t square by 2 sigma square into phi t. Now, what is phi t? Phi t is the characteristic function corresponding to capital F. So, minus infinity to infinity to the power I t mu d f u dt. Just a little bit of algebra we will get immediately. Minus infinity to infinity integral of 1 by 2 pi integration minus infinity to infinity, this e to the power I t into u minus x into e to the power minus t square by 2 sigma square dt dfu. So, we are basically changing the order of integral, obviously by Fubini's theorem, and we can write this entire thing as minus infinity to infinity a u x divided by root over 2 pi sigma into dfu. If we do just simplification, we will see that this a u x is nothing but the characteristic function of a normal 0 1 by sigma square variable at t equals to u minus x. Therefore, this original integral 1 by 2 pi minus infinity to infinity e to the power minus I t x phi sigma t dt equals to integration minus infinity to infinity 1 by root over 2 pi sigma into e to the power minus u minus x whole square by 2 sigma square dfu, which is nothing but the convolution of phi sigma with f, that is, which is nothing but the density of z. Hence, we can immediately write that 1 by 2 pi minus infinity to infinity e to the power minus I t x e to the power minus t square by 2 sigma square into phi t. This quantity is nothing but the density of capital F sigma, which we denote by small f sigma x, say. So, this result we get just by simplification and using the convolution. Now, integrating with respect to x from alpha to beta and obviously using Fubini's theorem. Actually, the proof of this theorem is repeated application of Fubini's theorem. So, this becomes 1 by 2 pi minus infinity to infinity e to the power minus t square by 2 sigma square into phi t into integration alpha to beta e to the power minus I t x dx dt. As we know that this entire quantity is f sigma, so we can immediately write, after changing order of integration by Fubini's theorem, that integration alpha to beta, this entire quantity is f sigma x dx, which is nothing but capital F sigma beta minus capital F sigma alpha. So, what we get is capital F sigma beta minus capital F sigma alpha is just this entire integral, and if we evaluate this integral, we will get e to the power, we will get this expression. So, capital F sigma beta minus capital F sigma alpha equals to 1 by 2 pi integration minus infinity to infinity e to the power minus t square by 2 sigma square into phi t into e to the power minus I t x beta minus e to the power minus I t x alpha by minus I t dt. If you recall the statement of the theorem, we are almost there. We get this expression exactly is there in the theorem. So, we are approaching towards the proof of the theorem, that is pretty clear from this step. Now, only thing is there, here is the presence of sigma square and here is the presence of sigma square, but all we want to show that we need something in terms of only f, not in f sigma, not in terms of f sigma. So, if we can show somehow, or if we can derive somehow from this expression how to get capital F beta or capital F alpha, or maybe their difference, we are through actually. So, enough to show that capital F beta minus capital F alpha is limit of sigma goes to 0 into this entire integral. Actually, this is basically the statement of the theorem, and obviously, we have to show that limit of sigma goes to 0 f sigma x should be equals to f x, because from here we can arrive at this stage for every continuity point of f. Now, if sigma is small, since sigma is tending to 0, we can always assume that sigma is a very small positive quantity. Then just applying Chebyshev's inequality for small sigma, we can get this theorem. Just a little bit of algebra manipulation, we can get this f of x minus epsilon less than equals to f of sigma x less than equals to f of x plus epsilon plus epsilon. Now, this epsilon is arbitrary. So, if we let epsilon to go to 0, we will get f of, from here if we get epsilon goes to 0, that means this quantity approaches to x from the left side. So, we can write capital F of x minus less than equals to capital F of sigma x less than equals to capital F of x plus if sigma is small, and therefore, we can immediately write as sigma goes to 0, capital F sigma x equals to capital F of x, because x we have assumed belongs to the set of continuity points of f. So, the equality holds as sigma goes to 0. So, that is the proof of the inversion theorem. So, basically we have used one convolution with a normal variable, forcefully we have done it, and then we let the sigma, let this sigma term to go to 0. We have used Chebyshev's inequality and Fubini's theorem many times finally to get the result. So, now we know how to get a distribution function from a characteristic function. So, let us consider one corollary. Suppose phi t is a characteristic function of the distribution function capital F, and this is absolutely integrable. That means, integration minus infinity to infinity mod of phi t dt less than infinity. In that case, if this holds, then this capital F is absolutely continuous with the density given by small f x equals to 1 by 2 pi minus infinity to infinity e to the power minus I t x into small phi t dt, and also f x is absolutely continuous. So, this result actually ensures that we can get, sometimes we can get the, if the density exists, that means, if the probability density function exists for a random variable, we can also get that density function from the characteristic function, provided of course, these conditions are satisfied. So, this gives a nice way to not only derive the distribution function, but under some conditions we can derive the PDF of the random variable, provided obviously it exists. Another corollary, although this is a corollary, but this sometimes can be stated as a uniqueness theorem. Basically, this says that f and phi determine each other. That means, whether phi determines f uniquely. So, by definition, phi equals to minus infinity to infinity e to the power I t x d f x, this determines f uniquely. So, that is the question. Now, suppose f 1 and f 2 are two distribution functions corresponding to phi, then we know by inversion theorem we can always write f 2 beta minus f 2 alpha equals to f 1 beta minus f 1 alpha, if alpha beta belongs to the set of intersection of the set of continuity points for f 1 as well as for f 2. Now, keeping alpha fixed, if we vary beta, so we can immediately get that f 2 alpha minus f 1 alpha equals to f 2 infinity, we can let beta to go to infinity, f 2 infinity minus f 1 infinity. Now, being distribution function, f 2 infinity is 1, f 1 infinity is also 1. So, this becomes 0. Hence, we can get f 2 alpha equals to f 1 alpha. Exactly similarly, we can also get f 2 beta equals to f 1 beta. And we have already known that since the set of discontinuity points is at most countable and the two distribution functions agree on a dense set on the real line, that means, this thing happens on the continuity points, and since the set of discontinuity points is only at most countable. So, the set of continuity points is a dense set on the real line, and the two distribution functions agree on a dense set of the real line, hence they must be identical, and so we get the uniqueness theorem, which states that f and phi determine each other and uniquely. So, let us consider the previous example of x j, where x j follows binomial 1 p, and we know that capital X has the characteristic function, which is q plus p into e to the power I t whole to the power n. So, the question was, does there always exist a distribution function corresponding to a characteristic function? Answer is naturally yes. Next question, if so, it is unique. So, the answer is naturally yes, based on the inversion theorem and the uniqueness theorem. So, immediately we can say that there exists a distribution function for which this would be q plus p into e to the power I t whole to the power n would be a characteristic function, and this characteristic function determines that particular distribution uniquely. And since we already know that this is the characteristic function of a binomial random variable with parameters n and p, we can immediately identify the distribution as the binomial random variable with parameter n and p. So, the conclusion is really very positive, that we can identify a distribution through its characteristic function in a unique way. So, from today's discussion, we have learned a few theorems on characteristic functions, which actually gives us the idea about the name, that means it really characterizes the distribution function. And interestingly, we have studied one major theorem known as inversion theorem. Inversion means that given a characteristic function, through this theorem or the statement of the theorem and the result, we can actually derive the distribution function, and more importantly we can do this in a unique way. That means, given a characteristic function, there exists a unique distribution function, and naturally we know that given a distribution function we can always find a characteristic function. So, naturally one determines the other, that means distribution function and characteristic function determine each other. So, this is a very important step forward towards determination or towards characterization of a distribution function through a function which is called characteristic functions. So, we will be discussing some more results, more theorems, and some results or theorems in probability, in the area of probability, that can be solved or proved through these characteristic functions.